In. Welcome back, everyone. I hope that you're doing great. I have our two panelists here ready for the last session of day one of Tartu Startup Day 2025. So for the next session, we're going to talk a little bit about quantum computing and is there quantum computing boom or bust? And for that, I would like to welcome our moderator, who is no stranger to this stage on the Deep Tech Lounge. So please give a big round of applause for Kalev Kaarna, now R&D Sales Manager at Metrosert.
Thank you.
And Kalev, I'll let you introduce Johannes.
So with me today is Johannes Heinsoo from Tartu, so back to the roots, quantum engineer who got the hardly earned degree and found out that there's nothing to do with it in Estonia. So now he's working in Finland at EQM, which is making quantum computers from 5 qubits for like student and education applications up to 50 and now soon 100, 150 qubits. And we just had a great session with Johannes and Teppo Seesto from IBM about quantum computing present and future. And I actually like to start here with what we ended there. That NVIDIA CEO recently said that very useful quantum computers are actually like 20 to 30 years in the future, and after that, the quantum computing stocks on the market plummeted. And everybody was looking at, okay, this is the end of quantum computing boom, and now it's quantum computing bust. But interesting thing is that NVIDIA CEO forgot to tell two things. One thing is that he forgot to tell what's very useful. That, and this is what we're going to talk with Johannes here, that what are the useful applications of quantum computing which is already in use, people are already getting benefits out of it. And the second thing the NVIDIA CEO forgot to tell is that NVIDIA is investing heavily into quantum computing. And you had a good example of it. That how do you know that NVIDIA is investing heavily into quantum?
Yeah, hi. Yeah, this example is definitely worth sharing because it also a little bit serves as a disclaimer to describe my background. So I studied in Switzerland in a technical university called ETH Zürich, and I met there a very talented lady who happened to also be, I think, a Swiss champion in figure skating. So a very hardworking and multi-talented person, and she was working for a professor who was a world-known like quantum information, like a quantum application theorist, like a computer scientist who was well known for debunking, for example, early claims by D-Wave and so on. So a very prominent location, and she got a Nature paper from her master thesis, I think, and later she was both of them, the professor and the person, were hired by Microsoft to build a quantum software platform there, and later we were all bought into different places. So Bettina Heim, who I'm talking about, she is now working for NVIDIA for a few years, has built a big software platform development team there, and they have an ambition to implement this sort of quantum software, quantum operating system, like Glue, which would allow abstract away hardware and run applications on it, and also like expose different backends, including a special backend implemented by NVIDIA, sold by NVIDIA. So they don't sell today quantum hardware, but they provide this operating system which can interface to other hardware providers and also to their classical hardware, which uses GPUs to efficiently simulate quantum hardware. So NVIDIA is in this hardware business, selling like fake quantum computers, and they have heavily invested into this team of building this operating system in between.
So it seems more that NVIDIA CEO had a very good scare tactic to get others off a gold mine he has discovered, and that probably he's investing not having like 20-year horizon, but he has a much shorter horizon what he's investing for. But let's dive into that. When we're talking about quantum computers, that maybe to our listeners, one thing to say that this is totally different logic of computing, because you use quantum mechanics properties that one energy bit or impulse or can be in multiple positions, which significantly increases your capabilities of building faster and more powerful computers.
Yeah, I like to summarize it by, like, people have maybe heard of these cats which can be dead and alive at the same time, and they will stress that this is possible. But what often is like forgotten from these stories, that there are many these dead and alive at the same time states. So these super precision states, there are many of them, and they can actually be distinguished. So into this extra space you have, into this extra possibilities, you can store information and process it. And the amount of these states grows exponentially with number of qubits. So if you have, for example, 2 qubits, you have suddenly 4 different superpositions. You can be in, for example, in a superposition of 0011 or superposition of 1001. So the number of extra superpositions grows exponentially with number of qubits, and this gives like a possible computational advantage. But to make use of this power is super hard. And this is because in the end of the computation, you want to come back to the classical world. Like what we consider information are bits, not qubits. What we consider a fact is something which is certain, not dead and alive at the same time, but you need a fact, you need to know. And the way we have defined a fact, this limits the output of the computation to be classical bits, which means that you have to come from this huge state space, exponentially big states with like astronomical number of possibilities, down back to your everyday world.
Where
and
things are, Donald Trump is a president or isn't the president.
Just one
of them can't be both of them.
Yeah, after elections, it's it will be determined. So this quantum measurement is this magical place, this election, this moment, special moment in time, and a special thing happens. Like all this rest of the quantum information is destroyed, and you have to really make your algorithm such that this useful information would be condensed into this whatever you get in the output. If you just trivially want to calculate everything in a superposition, your outputs of the computation will be like random. They won't correlate with what you actually wanted to know, and it won't be useful.
So, which means also that we are used to interact with computers directly, like with our PCs and laptops, but with quantum computers we have to use the traditional computer programs to be able to communicate with quantum computers. So that's one challenge, and then the other challenge is, as we are dealing with quantum mechanics, very small bits and pieces of physics, then they are very sensitive to all kinds of interferences, and which means that you have to have refrigerators, almost near zero environment, where the small particles
even
behave.
Small piece of energy.
Behave the same way, and can't be like too many waves or loud noises or stuff which will interfere with your calculations. So we're talking about error rate.
But I'd like to maybe debunk both of the things you said.
Okay.
Like you don't actually interact directly with the computer, right?
Okay.
My mother did, but I think you're too young for that. So what she had to do was punch holes in perfo cards. So she was actually like writing bits, right? And we don't, right? Like you type on keyboard, and this is already converted into bits by some ASCII, which only nerds know, right? So it's far from direct interaction, and today the technology has matured to the level of reliability such that you can have one, I don't know, sometimes fall into a toilet and afterwards it still works.
Okay.
But when my mom was doing her first interaction with computers, she had to tap on lamps to make them the switches actually switch, and that's a bit similar.
So this is one myth. What's the second myth?
Yeah, the second first myth was that we interact directly, and the second one is that that classical computers are reliable. Like they are not reliable out of some principle, but just because the technology is mature. And that's also the fundamental reason why quantum computers today are
not so reliable.
Technical readiness level is super low, because you need so many components to work in harmony, and if any of them fails or whatever, it's a problem. And as you said, this information is stored into like very sensitive, very small piece of energy. They are very sensitive to any other quanta around, like a single photon comes and can perturb it. So they are sensitive and immature. So we have to like make them more mature such that they would survive even when they are so sensitive.
Yeah. So the challenge is that we want to increase the number of qubits, like going from 150 to maybe thousands and millions. And the second thing is that we want to get the error rate down.
Yep.
And the third thing is that these are called like gates, that how many operations one quantum computer can do. Like basically, like I think of it like how big memory it is, how much stuff I can give it to calculate. That we want to increase the number of operations one computer can run.
But I think this number of operations is another way of looking at how good a gate is. Like if gates are bad, then if you use many of them, computation will likely not succeed. So the number of gates you can do is actually just a different way of telling how good the gates are. But in total, your useful computational volume is determined by the number of qubits, the depth of your calculation, like how good the gates are, and also how quick the gates are. Because today the quantum transistor has not yet been invented. There's like 10 different platforms which you can use to build a quantum computer. We use superconducting circuits, and there's also different variants of them, so we don't know which of them.
So it's a standards war, like which approach will win.
Yeah, and we don't know. So and one of the leading contenders are trapped ions, like individual ions, which are stored in electromagnetic traps, and they today, for example, would provide you higher quality gates, but they are like 3 orders of magnitude slower.
Okay.
So in a short term, yes, you can have a higher computational volume because they are high fidelity, but in the end, the applications, like factoring some large numbers or simulating some complex quantum molecule, it's going to be, you actually care if the application runs a day or 3 orders of magnitude longer, like a year or tens of years, right? So in the end, the speed matters, and if you want to, like this is one of the strengths of the superconducting circuits, is that they are like faster than other good alternatives, like multiple orders of magnitude faster.
And this discussion what we had before is that like a hardware is getting to the level that 150 qubits is enough for certain applications in drug development and folding the proteins. What is missing is getting the error rate down to the right level, and also that the other thing is that the qubits, how many connections the qubits have to each other, the more you have, the less the error rate you have and faster the computer is.
Like if your information or computation can more quickly spread around on your processor, if like you have a better network where information can propagate faster,
you have
will
6.
Speed up the computation. It's an effective way of speeding up a computation is to have higher connectivity.
Yeah, so these are the tasks, and now the statement is from IBM was that in all the theory is there, that now it's more like engineering problem. What you said was that yes, the theory is there, it's just out of the labs, so it's still like semi-engineering, semi-theory problem, because like you are dragging the research results to your company and implementing this stuff, but it's still more closer to the engineering problem, and we can predict that, and like IBM said that in 2 years they have error rate to a level that guys doing the Finnish company who is building the drug R&D tool for drug discovery and putting it to fluid dynamics, putting it to quantum computing, that they say that it's good enough that they can start offering commercial products. So do you see also that this hardware problem is going to be solved in the next, let's say, 4 years, that we can start to use it already?
Well, so the systems today have usages, like they are already big enough such that you can run the correct algorithm, the algorithm of the future, but on a very small data set, for example. You can factor numbers, but quite small numbers.
And which goes to that, we discussed that applications of quantum, that quantum is not good for anything, everything, that there are certain areas it's better than cloud computing. One is the simulations. The second area is about like a AI, it just does it better, like a machine learning, it's better, more powerful, you can solve problems faster. And the third is optimization exercises, supply chains and stuff.
You can test all of these algorithms today, and this is already in like one of the applications you already have today. Like it doesn't give you all the returns or whatever, but it is an application. And over time, hardware is going to continuously get better, and number of applications is going to grow over time. And I think it's going like Tallinn is never ready, quantum computer development of quantum computers is never ready. It will always get better and better and better. And exactly like we are exactly on this threshold where devices are large enough and almost powerful enough. They just need just a tiny bit better, and then we can really start enabling scientific breakthroughs. So this we are very, very close to big academic advantage. But likely industrial problems, we have studied, our theorists have studied are slightly bigger, so you need even bigger systems. And then this is likely above this threshold where error correction also needs to kick in. And this will make everything like order of magnitude more expensive or more complicated, so this is going to delay these things by maybe a decade or two.
So if we talk that there are challenges which are going to be solved in hardware, you need to like go into more parallel compute and this stuff, and where would you recommend the startups who want to go to a quantum field right now? Where do you see the opportunities for the next wave of startups? You also said that some of the opportunities are already missed.
Yeah. Well, yeah, some opportunities missed and some are in the future, but of course also these established electronics providers who invested in the past and have already cashed out. You can still be an underdog and be even better than them. For example, the electronics we use is around 4 times cheaper than the commercial electronics available and developed in Tartu. There's an engineering house which is our subcontractor, like it's not our goal and purpose, because productizing something is expensive, but in principle there's an opportunity to be a hardware provider still today if you manage to like productize this cheaper version. But it definitely requires you to understand how quantum computer works, such that you could understand how to solve a problem, how to be a provider, how to be one who sells a shovel to the gold diggers. You need to understand how it works, and one way how to learn it is like I think also Estonia should buy one of these systems, such that university students could learn how it works, would learn every component, and would become an expert in one of them and replace it with something better, and then be a shovel seller to the industry of the future.
But also that as hardware is maturing, then the next level would be the operation systems, how to manage it, and then the application software systems.
Yes.
That this would be, as right now, there are not too many hardware PC manufacturers anymore, that this market will shrink, but there are like hundreds and thousands of different software companies offering applications to run on it. So probably, most likely, my bet is that something similar happens also in quantum computing.
Yeah. So there's like a stack: hardware, low-level software, high-level software, and you definitely can replace any of them. You can make an investment that your strategy could be to contribute any of the layers of this stack, and none of them is ready. Like today, it's also very early to say like which of the hardware providers will survive because, like as I told you, we haven't picked what is the transition of the future. Yeah.
It's like VHS and Betamax with standard competition.
Or like even which type of hardware, right? Like, are you gonna use photons, or ions, or atoms, or defects in diamonds, or superconducting circuits, and even superconducting circuits, there's many types. There are ones which are charge heavy and ones which are current heavy.
So options are
and they're all competing, and there's like tens of commercial companies in each of these domains. Each one of them has few large players who are trying to commercialize this technology, and this natural selection is going to choose which of the physical system is going to survive. We work with superconducting qubits.
So what's your last recommendation for startups wanting to enter quantum ecosystem and do something there?
Yeah, I think if you're ready to contribute to quantum or like to be part of this stack, you likely know.
Okay.
Because like if you have a super hard computational problem, you might likely already know that theoretically this your specific problem can be done more optimally on a quantum computer. Or like if you have expertise in like microwave engineering or something, then I mean come and talk to me, and you possibly can contribute. so if it's obvious that you can, you will likely know about it. And if you don't know about it, then first step is to start to learn about it. There's so many opportunities that it's hard to impossible to summarize them shortly.
Awesome. So go talk to people like you, and through that learn and use other opportunities to learn about these new opportunities, what's going to happen in quantum, because of different reasons like cybersecurity and post-quantum cryptography and this stuff, that investments are so heavy that there will be new winners.
And there also likely is going to be a winter before winners come out, but but if you prepare well, you're going to survive the winter, as we will.
Thank you, Johannes, for this podcast, and thank you all the listeners, and I hope you learned something new, and see you around.